Bye, Nancy. Yeah, I'll help you get some more guests.
Hi, Nancy.
Yeah. What? Oh well.
I will help you get more guests.
Yes.
Bye. Miss you. I wonder why this is happening. Like it worked. You're able to come into Zoom. Rendezvous is just like Zoom. It uses your video device, uses your audio device.
I don't know.
Why wouldn't it work?
Well, everybody could see me but Pamela, so. And I guess she's the important one to get me on the show, right?
Yeah.
So.
I don't understand.
Okay, if we're still stretched for time at the end, I can definitely talk a bit about the satellite disruption, because I think I get the gist of it.
I have a pretty good list going here too, Fraser, so.
Astronomers use Gaia to track stars that were from the galaxy that got gobbled up by the Milky Way.
Yeah, and they use like some technique to group the stars according to which accretion event they belong to, and they're able to identify a new group. Be identified to a new.
I see. Did they do like the actual chemistry?
Can I put you live while you talk?
Yeah, totally. Because that's the thing that's been really interesting is matching Gaia with some of these chemical like spectroscopy surveys that are being done as well.
Right, exactly.
And you can really just see the different generations and the different families of stars, because I guess a whole galaxy can generate stars with similar chemicals in them.
Right, because since we're talking about dwarf galaxies here, so like there aren't that many. Like the star formation history within like a single dwarf galaxy is rather similar. It's quite homogeneous.
Right.
So each dwarf galaxy will sort of bring about its own unique chemical environment. And so if they're depositing onto the Milky Way and their stars are splattered across the stellar halo, they should share a similar kinematics, but also that common chemistry. So that's how you're able to sort of blend the two, kinematic and chemical, in order to identify these groups.
I wonder if we can ever get to a point where you could just unravel the whole Milky Way back in time.
Well, yeah. Sorry.
Okay. But farther, like obviously, like right now, they're starting to detect all of these ancient collisions. But I wonder if you could just like completely unroll the whole process. I bet you could. I mean, eventually, that's where this is going. Is you eventually end up with the 72 dwarf galaxies that came together almost like a family tree of the Milky Way. Would be really neat. Hey, we're live. I'm gonna say hi to some people. Hello to Fifth Dimension, Alan, Series K Lee, Corey S, Ian Farquharan, Jim Ashby, John Suffield, Johnny J, Kim Barron, Kira H, Larry King, Nancy Graziano, Popcorn Power, Roger Haskins, Canadian Space Advocate, Trey Harmon, Tropical Tom Garcia. That's it. Hey everyone, welcome. Sorry for the late start. We'll just get started. Just to warn you, we don't have a guest this week, and we might have to start a little short. So I'll just keep an eye on things. And if we tend to talk too much anyway, but if for some reason we find ourselves starting to wrap up, I may just shorten the show randomly. So just be prepared emotionally for that. All right. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, February 23rd, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about a gigantic galactic shockwave, supermassive black hole that was hiding, what to see in the sky, including that UFO, I mean Venus, how James Webb detect alien civilizations, and a simulation of the universe that matches reality. Joining me this week, let's see, who do we have? We've got Alan Versfeld. Hey, Alan.
Hey, how are you doing? It's good to be back.
Good. I, as always, I really got to appreciate the fact that it is, I don't know, like 4 a.m. for you. So you are a hero to us all.
I am a hero. Yes, it is very
Yeah.
late and I'm tired. But I'll put on a good face.
Yeah. We got Chris Carr. Hey, Chris.
Hello, happy to be here, Fraser.
And we've got, I can't even, okay, we got Pam Hoffman. Hey, Pam. We're having some technical issues. And so Pam, well, Alan and Chris in my mind are sort of people, sort of full screen size people. We had to work with a technical hitch to get Pam in. And so she's like this tiny little portion of a tiny little portion in the corner. So I could just, you're like this big on my screen, Pam. But I hope the audience, you're the regular size. All right. Before we get into this week's news, I want to give a huge shout out and thank you to our good friends of the Weekly Space Hangout crew. They're our friends, our fans, our executive producers. They call the shots. We do what they say. And if you want that kind of ultimate cosmic power, join the community. Go to wshcrew.space and they will hook you up and give you all the information you need to become an executive space producer. All right, let's get on to this week's news. Ellen,
Hi.
let's talk about this monster shockwave.
Yes, so these shockwaves when galaxies.
Hold on, stop.
Galaxy merge.
Alan, just stop for 1 second.
Yeah.
Your Pamela, his sound level is quite low, and people on live are saying it's also. I thought it was just me, but he's definitely. Yeah, if you can raise his volume, that would be great.
How do I sound now?
A little louder.
And now?
Better.
Okay.
Okay, so you should be louder now. So
Okay. Is this a little bit better?
yeah, totally.
Oh, perfect. Okay. Yes. So basically, what we've got is the Meerkat telescope, the precursor to the SKA, has collected some data in 2018, and I've noticed this is often the case with these Meerkat stories. They seem to be really enjoying the telescope and just gathering data, and then spending quite a lot of time analyzing it, and then releasing these results. They were looking at a galaxy merger, Abel 3667, which is quite far in the southern sky. So it's one of the few telescopes that can see it at all. This cluster is quite big. I keep saying cluster. The collection of galaxies clashing are quite big. If I've done my conversion from exponent slide, it's about 700 trillion solar masses. 7 times 10 to the 14, that's a lot, you know.
It's a lot,
yeah. And in the process of colliding, they've sent out shockwaves through the interstellar medium, moving at about 1,200 or so kilometers per second.
So sorry, we're getting echo apparently. So for everyone else,
I'm fixing it.
Muted. Okay. But I'm not.
So,
Hold on, let's just give. Tell me when you got to fix Pamela. Because it'll probably drive people.
I should probably make it sound so you can hear if the echo's gone.
Sorry, I was muted. It's fixed.
Okay, excellent. All right,
Okay,
please
so
continue. It should be fixed.
Okay, so these shockwaves moving through the interstellar medium they're not just pretty to look at, but they give useful information about the interstellar medium, not just the heat, but also magnetic fields and what have you. Like I was saying on Twitter earlier today,
Oh,
the classic
people are saying
audience
not
question.
fixed, Pamela.
Oh, goodness. I'll just keep talking while you work on that.
Well, you know what? It'll drive everyone crazy.
Then I'll silence it.
Seriously, Lee saying, "Shh, I like it."
I don't know why.
Just pretend I'm reading this out in a basketball stadium.
Can't think of why we're getting an echo.
You found it.
Okay, it's fixed.
Okay,
you can
great.
fix it, or it is fixed. Okay.
All right.
Okay. How about now? Hold on, we're gonna wait. There, people are saying normal. Okay, great.
Oh,
Please
so nice
continue.
To be normal.
You can do it.
Where was I? Oh, yeah. So these shockwaves are revealing all sorts of extra characteristics, and I was saying on Twitter earlier, what's the classic question if you really want to irritate somebody presenting their work at an astronomy conference? Have you considered magnetic fields? And yes, they have. They have. That's what we're looking at.
Right.
Oh goodness! I'm so sorry. I've lost my train of thought here.
And so what is it? So what did they see? They saw this gigantic structure in the meerkat.
Yeah. So the image we were looking at originally, that is one of the two lobes of the shockwave that have come up. You can see on the top there, they've for scale, for real scale, they've put a tidal image of the Milky Way. But for visual scale on the sky, if I understand right, it's about a little bit larger than the full moon in the sky, this lobe that we're seeing here.
Wow.
So it's very big. I mean, this is, wow. Yeah, I'm sorry, I've lost my train of thought. I've forgotten exactly how many megaparsecs across we're looking, but it's a lot.
I recall it being like 6.5 million light years. So,
Yeah.
I think Chris, I'm sure, could do million light years to megaparsecs in his head. What, 2 megaparsecs? Is that right? Ish, but 6.5 million light years. So it's
I think
it's gigantic, right? Like it would absorb. You could put the Milky Way and Andromeda in that blob and have room to spare. That's how big that thing is.
Yeah.
It's gigantic. Like, say Andromeda's whatever, 2.5 million light years away from us. So it's mind-bendingly large. And it is. And so what do they think is causing this shockwave?
Well, this would then be directly a result from the merger. There's a second image which shows a wider view. I'm not sure if Pamela can skip to that one. This is directly from the impact of the two. We think we were taught when we were younger about how galaxies collide, and it's just the old days view was just these stars serenely passing by each other, and then we started modeling it correctly. And no, there's all these gravitational interactions, but there's also the medium in between the stars, which interacts and it collides, and so we have these shockwaves moving out through the interstellar medium, and that stirs that material up and generates a lot of magnetic fields, quite strong magnetic fields that polarizes light passing through it, and so we get these complex structures which we can be quite nice. Oh, this image is actually from a different news item.
Don't
look
at the news item. Don't look at the picture.
I'll cover my screen. There we go. Yeah, that's the one. That's the correct one. Yeah. And this is just spreading out from that merger. So whatever processes are going on within these two galaxies as they merge, this is now the impact spreading out through the interstellar medium, which, what's the density? It's low. It's something like a few hundred atoms per cubic centimeter or something on those lines. It's quite a thing. I mean, they say it's moving at about twice the speed of sound through the interstellar medium, which I don't even know what that means. I mean, I know what it means, but it's just strange to think of there being a Mach number for something traveling through the void between galaxies.
Yeah, yeah.
There we have
So-
it.
It's producing a shock then, right? If it's traveling
Yes.
faster than the. Okay, right.
So
Yes,
so
yeah.
Chris, this idea of like a gigantic shock, what impact, like I know that just within a galaxy you can have supernova trigger collapses of stars.
hmm
And so you've got this almost like replicated at a galactic scale. Would you get a similar situation where um uh, would this cause some effect galactically, extragalactically?
So in this case, if I understand, the shock is propagating into.
In the intergalactic medium as a result of a giant galaxy collision or galaxy, so you got two galaxies colliding with each other, and then
Mhm.
the shock is propagating outward from this region.
Okay,
Would
right.
this have some impact on their environment?
Right. So if you have the shock that's propagating outward at like faster than the speed of sound within that medium, then it can have this effect of sort of sweeping up the surrounding gas that it's encountering, and then over time, as that shock eventually starts to cool down, the dense clumps that are along the shock front may sort of condense to form these sort of pockets of gas, which in the case of a galaxy, though, those pockets of gas could be places where star formation could form. But in the case with the intergalactic medium, and they could just be just pockets of gas that could eventually be detectable once the shock subsides.
And I wonder if they went through a galaxy, if
Like-
that shock went through another galaxy.
Right. So it would really depend on how the self-gravitating the galaxy is. So if it was like a loosely bound dwarf galaxy that was encountering the shock as it rammed through it, then it very likely that the dwarf could be evaporated or entirely disrupted by an event like that.
Yeah, that's really interesting. So was this an accident, Alan? Like they just weren't expecting to see this?
No, they were looking for it. These artifacts have been seen before, but SKA. Why do I keep calling it SKA? I'm just so excited. Meerkat is so is able to look with such high resolution and at such a wide angular resolution, but such a wide field of view. They're able to get details that have never been seen before. If we were able to zoom in on this, there's very, very fine structures and lines in these structures. So it's a lot more information to try and piece together exactly what's going on with these.
It's fascinating that you've got this structure that is as big as the full moon in the sky, which is big. And yet it's the kind of thing that nobody had seen until now because they just didn't have as sensitive an instrument as Meerkat. But now we have Meerkat, and suddenly these sorts of features are going to start to appear in the sky. You can imagine them doing some all sky survey with Meerkat with the square kilometer array eventually, and the whole universe is going to look textured. It's going to look different because you're going to see these giant shock waves and clusters and just stuff that we just didn't have the sensitivity to see before.
It's it's going to change everything. I'm really looking forward to. I think this will be the next round of. Remember how Hubble changed the public perception of the world with those amazing multicolored images of nebulae and so on. Now we can show a whole new class of, well, not just the pretty pictures. I mean, there's going to be real science, obviously, but it's going to be very exciting to see what comes out.
Yeah, really interesting. All right, Pam, Tell us about what we can see.
All of it is like, wow, so cool.
Well, you've got to
So-
choose.
What was that?
You've got to choose right now. You've got to choose. Talk about one thing coherently, as opposed to just jumping around all of the things that you're excited about at this very moment.
Well, right now I'm going to talk about things that you can go and do. How's that?
I love it.
All right. So
I've
I
got
think the
time.
major.
I like to do things.
Yay! Cool. So right now, I think the major attraction is Venus. It's high, it's bright, it's in the morning. You want to get up early to see it. And I do have some other things that are kind of happening. Of course, we've got the show tonight, and I have a show on Fridays, but there's a cool conference coming up. And I heard about a meteor shower in the Southern Hemisphere. It's like by the Southern Cross. The next one here in the Northern Hemisphere will be in April. I'll talk about that later. I found a couple of new contests. I'm going to talk about 4 altogether. The Globe at Night begins another project, and there are 15 conjunctions. Only I think 4 are worth mentioning, really. So I'm going to talk about contests, Pamela. The first one is Women and Girls in Astronomy. It's part of the International Astronomical Union. And I love what they say. Share an image of your imagined astronomer for a chance to win a telescope. This is for youth up to age 12. I think it's worldwide, but the deadline is March 1st, so go fast. Then the European Space Agency has that's the URL to send your image to. The European Space Agency has Build Your Web Challenge, and you can make this out of anything. I've seen one with food. But there's the website. You want to go and submit your challenge. This is for age range 6 through 19. And there's the food one. I don't know that there's any restriction as far as like country goes. So anywhere in the world, try it out. The design moon digging robots is still going. Lunabotics Junior. This is a Lunabotics Junior contest. NASA is sponsoring this, and you can enter art or you can be a judge. I have talked about this before. The winner from each category will be announced March 29th. Then we have nominate a student with perseverance. The second round is still open until the 28th of February. This is for 6th through 8th graders in the United States for public schools, private schools, and home schools. And there's some really cool prizes. There's 4 rounds total. This is the second one. Now we're at Globe at Night. Globe at Night has projects that last about 10 days each. February 22nd, yesterday started this next one, and it goes to March the 3rd. In both the Southern Hemisphere and the Northern Hemisphere, they're asking you to go out at night, look at Orion, take some pictures, and report on how in depth you can see, how many stars you can see in your area. They've actually focused on Orion for several projects now, so I'm thinking they should have good information. If you don't mind showing the next slide, Pamela, I did a little digging, and this is part of their results. I was like, well, what are they doing with all this, and what can we see from what they're doing? Next is just going to be talking about, like, first quarter moon is tonight. On the 27th, Venus and the moon are in conjunction. And again, most of the planetary action is in the morning right now. The moon's very small, though, and waning, but you can see, I think maybe Mercury and the moon are in conjunction on February 28th. I think you can see Mercury. The moon will be pretty small. And March the 2nd is the new moon. They say Mercury and Saturn are in conjunction that day, too. I don't know what you're going to see. Saturn, I think, is pretty small right now. Then there's a conference. I think I have a slide for that. March the 7th is is the 53rd Lunar and Planetary Science Conference. It'll be the 7th through the 11th, and they're doing something different. It's hybrid. I think most of the past ones have been all in person. It sounds like you're going to be able to meet together in person and catch it online as well. So check that out. Then we're back to March the 10th is the first quarter moon. March 12th, Venus and Mars are in conjunction. On the 18th is the full worm moon. I love the names
full
of them.
worm moon.
Full worm moon, yeah. Of course, each one has a couple of different names. Well, sometimes, like the Northern American Indians had names for the moons sometimes. And then, of course, we name them too. March 20th, Mercury and Jupiter in conjunction. And Venus is at its greatest western elongation. So it'll be highest in the sky. And the middle of this month, it was the brightest. So it's going to be pretty darn interesting to see as far as going outside and looking. It's in the morning though. March the 20th is also the equinox. And I think we just say the March equinox now because, of course, in the northern hemisphere, it means that spring is coming, and in the southern hemisphere, it's a fall event. So let's see. Oh, and there is another globe at night. It starts on March 23rd. I'm going to talk about that next time because I've been invited to come back on March the 23rd, and we can do it then.
Awesome.
Thanks.
So I've had a couple of people telling me they're seeing this UFO Venus. Have you seen it yet?
You know, it's in the morning.
Morning?
I'm an evening person generally, so I haven't seen it. But yeah, Venus is sometimes mistaken for a UFO. It's so bright, and if it's very low on the horizon, it kind of gets that elongation look because it's going, it's passing through more atmosphere in that, low horizon position than if it were, think about it. If it's straight overhead, it's kind of the least amount of atmosphere between us and the object. And if it's on the horizon, and you'll see the sun do this too, it kind of gets elongated. But yeah, if you see Venus like that and it's super bright like it's no surprise people are going, hey, what is that? Is that a UFO?
It's funny because I've had a couple of people tell me, they're like, oh, what's that really bright star in the morning? I know it's not Venus, but what is it?
It's like, Venus.
Yeah,
because none of the other ones are even anywhere near it. They said negative 4.9 the middle of this month, just a few days past. That's like super bright.
Yeah. Alan, you could like just stay up just a few more hours and see Venus.
He says no.
Just skip going to bed. No sale. You're gonna go to bed. All right.
But it's there. It's there. All right. If you want.
Awesome. All right. Well, thanks, Pam.
You should.
All right, Chris. So let's talk about, this is cool. Let's talk about James Webb detecting other civilizations. We
nice change of pace, I think.
Yeah. Why learn about the first galaxies of the universe when we can find out if there's alien civilizations destroying their atmosphere out there?
I think that's a much more exciting, prime directive, for the mission.
Yeah.
Yeah. So by this point, we all know about the James Webb Telescope, NASA's big new flagship that launched into space last December and is stationed now at the L2 Lagrange point. After what has been an incredible sequence of events since launch, even to this point, I'm still amazed that everything has gone perfectly to plan, even better. I think it has excess fuel now, such that it can now exist years beyond its initial projection of 10 years. So that's happy for me as someone who I'm sure will be looking for employment during that time. Know that there's a telescope out there constantly pumping out data is good for everyone. So and the telescope is now going through a series of alignments, adjusting the positions of its mirrors in order to sort of resolve its imaging capacity. So at this current pace, JWST is expected to be fully operational by this summer. It will begin its great mission to explore the distant universe. JWST is expected to do a lot of wonderful things, but one uniquely interesting proposition that has been brought forward by a team of researchers out of the Blue Marble Space Institute and NASA Goddard is that JWST could be used to look for signs of intelligent life in the galaxy by the traces of certain chemicals in the atmospheres of exoplanets. So if planets were to possess life, intelligent or otherwise, these life forms may produce certain chemicals that could be detectable in their atmospheres. This is the motivation behind the search for biosignatures in the case of life generally, or technosignatures, which is for traces of technology from potentially intelligent civilizations. So in the case of biosignatures, you can think of examples like the recent claim of detecting phosphine gas in Venus from a few years back, or the detection of methane in the atmosphere of Mars. The thinking goes that since these are chemicals that we associate with biological mechanisms here on Earth, their detection on other planets may be indicative of life elsewhere. That's the chain of reasoning. This paper applied that thinking to chemical pollutants that are a direct byproduct of industrial society, such as chlorofluorocarbons, CFCs. Now, here on Earth, CFCs have been largely banned due to their ability to deplete the ozone layer. This is part of the Montreal Protocol, I believe. But they still exist in measurable concentrations to this day. I think I have a plot for that on the next slide. Oh, other direction. I think yeah, there we go. Where it shows the concentrations of CFC in the atmosphere over time. And this is for the two particular CFCs that the authors were interested in looking at for the study. And you can see the concentrations of CFCs go up until around, it's hard for me to see on the screen, but I think it's on the 80s or so, where the Montreal Protocol goes into effect, and then they go on this steep decline. But still to say that the CFCs do still exist in the atmosphere, and who's to say that an industrial society somewhere else out in the cosmos didn't also make bad decisions and pollute their atmosphere
Right.
as well? Or perhaps ozone depletion isn't a problem for them, and then there was never really a reason to reduce their CFCs. So I think that possibility creates this interesting idea of looking for these sorts of pollutants out in other planets' atmospheres. And so how they actually went about this is, in this study, is through detecting, I guess backtrack a bit, detecting the absorption signature from CFCs using JWST requires that the host star not be too bright, such that it drowns out the signal. This is like a very trace signature that you're looking for. So the authors of this paper focused exclusively on M dwarf stars, like the TRAPPIST-1 system, a very recent one that will be a huge subject of interest for those in the exoplanets community. Particularly TRAPPIST-1e, which is one of the planets that is in the habitable zone of TRAPPIST, and has sort of galvanized the most attention. So they developed climate models for TRAPPIST-E within the system with varying concentrations of CFCs with respect to the present day Earth's quantity. So if the amount of CFCs were equivalent to Earth today, or if they were double, or if they were triple, or would you be able to detect that amount of CFCs given the resolution of the spectrometer, which will be on JWST? And quite interestingly, they found that the detectability of CFCs is quite sensitive to the noise level of the JWST spectrometer. So assuming fairly optimistic but realistic noise floors of about 10 parts per million. And by noise floor, you just mean like if your measurement goes below this point, then it's so steeped within sort of instrumental error that you can't really say anything conclusively. So if you were to reach a noise floor of 10 parts per million, which is optimistic but realistic, one could detect Earth-level CFC concentrations with 100 to 300 hours of telescope time, which may sound like a lot, but that's less. But that's less than the time it took to image the Ultra Hubble Deep Field. So it's perfectly like in line with what a telescope like this could do.
And it's it's perfectly reasonable that they're going to put that much time into observing the TRAPPIST system.
Oh yeah, absolutely.
Yeah. Like
Yeah.
there is no better target. Like people always ask me, like, which target would you like to see James Webb tackle? And I just say TRAPPIST. Like TRAPPIST has everything going for it. It's got planets inside, within, and outside the habitable zone. It has the star is not too bright. To observe those planets will give us a wealth of information. And it's incredible to think that one of those things that it could see might be chlorofluorocarbons in the atmosphere of one of those worlds, that James Webb can do this. And it would just be a side effect of them observing as they do their detailed observations of these worlds.
Oh yeah, exactly. Like by looking for CFCs does not detract from like the quote unquote like real like scientific mission of studying these planets. Like there's no it's pretty much like something you just tack on to the side when you in your spectral analysis of everything else going on in the atmosphere. This is something that that could also be of interest that you should be looking for. And in 100 to 300 hours of telescope time, that's perfectly doable. And
Yeah.
and it really does inspire like a lot of thinking about of how humanity is sort of really getting close to be able to look for realistic technosignatures out there.
And how would like the discovery of chlorofluorocarbons compare to other, say, biosignatures that astronomers are thinking about? I mean, we've heard, maybe they'd see methane, maybe they'll see ozone, maybe they'll see carbon dioxide, water, whatever. But if you see chlorofluorocarbons, like, is that a almost certainty that you've got life there?
Of course, scientists never deal in absolutes, but I think like a detection of CFCs would be quite significant, more so than a lot of these other biosignatures, because it's incredibly hard to produce CFCs by purely natural means.
Right.
As far as I know, I don't know. I'm not sure if there actually is any process that allows.
Yeah,
you
I
to
don't
do
think it's
CFCs.
possible.
Like,
Yeah.
without some sort of intelligence behind it.
Yeah,
So
cows burping refrigerant. I don't think it happens like that.
Yeah. So I think CFCs are really kind of the golden goose for technosignatures and why there's a lot of interest. It's important to note that they do mention that if the noise floor is higher, if instead of 10 parts per million, if it's 50 parts per million, which would be very conservative, and we expect JWST to be better than that. But if it were to be a lot higher, then even concentrations 5 times that of the current level on Earth would not be detectable. So it really comes down to the noise level that we're able to achieve with the spectrometer on JWST, which will make these observations possible.
Right, and that is still a bit of an unknown.
Yeah, exactly.
Fantastic. All right, Alan, let's talk about your second story.
Yes. Okay, so this is all about active galactic nuclei. And I am unmuted this time.
Yep.
Great.
Yep, we hear you.
Okay, so so basically this is new data coming from a large team of scientists using the VLTI in the Atacama Desert, looking at M77. And they were trying to understand exactly what is going on to make that nucleus active. Because some AGNs are extremely bright visually, it's quasars. Some give these big pulses of radio energy, and some are quite muted, like this one. So there is an existing model, a unified model, which says that these are all the same thing. It's all the same process with large amounts of dust falling into black holes, generating a lot of energy. But it depends on our viewpoint. Is it pointing at us, or are you looking at it from the side, or what have you? And this was an attempt to try and resolve through those through the dust clouds and confirm exactly what's happening there. And that's basically what they've done. Using the VLTI, looking at a number of different infrared wavelengths, able to resolve the basic structure within that area, Because that was always part of the question: is how do we actually know? We've hypothesized, we've seen the dust is warm in the past, but is it possible to hide a black hole like that, a big one like that? And the spoiler is yes, it is, and the model is true. Well, again, like you said, there's no absolutes, but it certainly seems to confirm the model. But yeah, the structure they picked out is that you've got a large, cloud of dust, and then within that, a very dense ring of dust with a black hole inside that.
Right.
So it's the infrared views to cut through the dust and basically build the structure. And it fits the model very closely. So we are looking at it through the side. The beaming out of energy is going out perpendicular to our line of sight, so it doesn't reach us. And we just see this warm, well, I'll say warm, I think it's about 1,000 kelvins or so. But, you know, I mean, this is space, yeah, it's warm. Dust. Glowing dimly as AGNs go. And so going forward, now the time is to repeat the process on other similar galaxies and see if this is really as universal as we think it is.
And so this is at the heart of M77.
Yeah.
Right. Okay. So I mean, this idea that there is a supermassive black hole at the heart of every galaxy, can't you just assume that there's a galaxy unless proven otherwise? I guess they couldn't see it. And so
I mean, Chris could probably give a better answer here, but my understanding is it wasn't always, that was a question, but it seems to be pretty much assumed now. I don't think there's any reason to doubt that anymore. Am I right?
Yeah, Chris, apart from, like, I know M33 doesn't have a supermassive black hole, but apart from that, they all seem to, right?
Yeah, so I think you're definitely right that there's this assumption that every galaxy sort of houses a supermassive black hole, and it seems that seems to certainly be the case for massive galaxies, but there is still a lot of debate within the community about like how far down the mass range does that assumption apply. So, because for example, I feel like it could be it's quite easy to imagine that there could be dwarf galaxies that don't possess a supermassive black hole, or the supermassive black hole was ejected somehow,
Right.
or or the galaxy went through some interaction that resulted in it being ripped away. So there's a lot of like uncertainties, I think, once you start pushing down to more exotic systems at the lower end of the mass range.
And I guess what's key here is that it's not just a supermassive black hole, but it's actually an active one. So it's actively feeding. Normally we call those quasars, but when they're not pointing at us and they're enshrouded in dust, they can be a little tricky to see. And I think what was the major discovery here is that they were able to actually peer through that dust and confirm that the supermassive black hole is there and it's actually actively feeding and blasting out material.
And in the same way as a quasar.
It is. I mean, it is a quasar. Yeah. It's just a quasar. Yeah. It's like, what is it? Like you've got Seyfert galaxies, quasars, and blazars, and they're really all just seeing the same object at different angles. So when you stare down the throat, you have to tell me if I'm wrong here, Chris. That's a blazar. And if you see it from the side, that's like a Seyfert, like a radio galaxy. And if you see it at a bit of an angle, that's a quasar. But I think I may have it wrong.
I actually don't remember.
Oh, okay. Well, then never mind. Everyone could just assume I'm right. But anyway, the point being that these different objects, they thought they were different things. And then they realized that it really just is, what's the geometry? Are you staring right down the throat of the active galactic nuclei? Are you seeing it edge on, or are you seeing it at a bit of an angle? And when you see it, there you go. Pamela's confirming for me. Yes. So Pamela's saying blazar down the throat, Seyfert type 1 and 2 are different angles from the side, and then a quasar is seen kind of, stupid bright and feeding. There you go. So it's interesting then to have a quasar, an active galactic nuclei, but have it be hidden. because we can see these things across the universe. And yet, here's one that's only, that's relatively close to us, and yet it was tricky to even see it.
Yeah, that was going to be my question. It's like how close is this?
47 million light years.
47. Okay. Yeah.
Yeah.
I mean, it's a Messier object. It's not that it's relatively bright.
Right.
15 megaparsecs. That's for you, Chris.
And what I like about this particular story is that this model is something I was taught in school. It was just taken for granted. Admittedly, undergraduate level, this is what they teach you. This is how it works, and this is always the case.
Right.
And now we're actually testing that, and yes, it is actually like that.
Right. Yeah. I mean, it's like here in the Milky Way, we had no idea what was at the heart of the Milky Way until the powerful radio and infrared telescopes came online and could actually clear through the gas and dust and actually see what was there. And we're so glad to have these different wavelengths that now let us see all of these different factors of the same thing. When you think about what we can see in the visible spectrum, it's actually just this tiny little slice of the whole electromagnetic spectrum. We're like almost completely blind if we just rely on what we can see with our own meat cameras.
Did you see those beautiful images of the galactic core that came out the past few weeks?
The ones from Meerkat.
Yeah.
Yeah. Alan presented those a couple of weeks ago. Yeah. Mind-bending.
But have you seen people have taken that same data and then just messed with the color palettes and brought out so much detail?
So here's the thing about that.
It's
and
actually
we're
my
going to totally
wallpaper
rabbit
now.
hole here for a second, but like that is a radio image. And so like when you look through papers, especially papers like maybe 10 years ago, and you look at pictures that were taken with a radio telescope, they're blobs. They're low resolution blobs with maybe some different colors to them, but they're blobs. And that's because the way a radio telescope works, it scans across the sky, has a few sensors, and not a lot of resolution. It's able to detect a lot, but not very high resolution. But Meerkat created what looked like a photograph, like an X-ray photograph of the heart of the Milky Way with these structures and filaments. And you look at it and go like, it's great, it's a picture, but you have to keep reminding yourself that is a radio image, not just a photograph of the Milky Way. And then you sort of imagine what comes next with the square kilometer array, that this is just table stakes for what comes next with what is going to be probably what is going to be it will stand side and the extremely large telescope as the greatest scientific instruments built by humanity. And this is your glimmer, your glimpse. Meerkat, like I can see why Alan keeps bringing us Meerkat stories every time, because it's so exciting to see. Like finally, people will take radio seriously. That's what matters. All right.
It's also just national pride, so
Oh yeah, I don't know. We talk about it a bit in Astronomy Cast, and Pamela just raves about Meerkat as sort of going back to first principles, coming up with a solution for a radio telescope that is just phenomenal. And then to see that as one pathfinder, and then see what they're doing with them, and having these two techniques stand side by side and then work together in concert for this larger telescope. It's really exciting. Yeah, the people behind Meerkat, I should really interview someone from Meerkat, have done a phenomenal job and created some really groundbreaking technology. It's amazing. All right, Chris, time for one last story.
Okay. Well, I guess we can talk about a possible new member to the family of dwarf galaxies of the Milky Way, if that's all right with you.
Yeah. Now, like a future member, like the largest small Magellanic Cloud, or a past member dismembered?
Yeah. Definitely like a crossed out member on the family tree.
Yeah.
Yeah. So as I'm sure we've discussed many times before, within like the current paradigm of how galaxies form, it's really through the buildup of smaller systems, uh, merging with other small systems, gradually building larger ones, and so eventually, you start in the late universe, you get these massive galaxies that we see today. And so it's not so that process is not any different for our own home, the Milky Way, which also had this process of gradual accretion of swallowing dwarf galaxies, building up the disk that we see today. However, this long historical process of accumulation does leave some evidence in the present day structures of the galaxy, namely in the stellar halo, which is this reserve of stars which are out there in the dark matter halo, which sort of gradually orbits the galaxy at its center. And within the stellar halo lies these populations which were fed into the galaxy from this history of accretion events. And so, by observing the stellar halo, we're getting we're really seeing stars that likely were not born in the Milky Way itself, but have these separate origins. And so, and through and with these like recent satellites like Gaia, we've really had the data to not only get a good kinematic portrait of these stars in the halo, but combining that with spectroscopy, we can combine our kinematic studies with our chemical studies in order to really deconstruct the information that's out there in the stellar halo. And so this recent work attempted to combine attempted to use the Gaia data in order to really use the kinematics from Gaia to isolate these different populations within the stellar halo, which are each the consequence of these different accretion events. And in this process, they've been able to identify I think like 6, potentially 7 different kinematic groups within the stellar halo. So these are stars that have similar orbits to them, which sort of is an indication of their different origins. Because like stellar streams, for example, like as these small galaxies are coming into the galaxy and they're being tidally stripped, if they were on a more circular orbit, then they'll kind of accrete stars as they're coming in, and so that accretion of stars maps out the orbit that the satellite was on, and that's kind of the mechanism that gives you these stellar streams out in the halo. And so these structures sort of allow you to identify these different accretion events. Right. And so of these 6 groups, sorry.
Oh, I was just going to say, and we were talking about this sort of before the show, just this idea that you could kind of roll back the history of the Milky Way and see when each one of these poor, unfortunate dwarf galaxies got gobbled up by the Milky Way and torn apart.
Oh yeah, exactly. And like of these like 6 or 7 groups, they were able to sort of pinpoint them to different accretion events. So of course there's like the familiar ones like the Gaia sausage, that's the major one. There's Sagittarius, there's Sequoia, and a few other like minor ones that aren't like the marquee names, but are definitely present. But the new one which was discovered through this work, they identified a new group that they call Pontus, which is meaning the sea. It's in Greek mythology. Pontus is the name of one of the first children of Gaia, the Greek goddess of Earth. So I guess it's rather fitting.
That's awesome. We've run out of time. I can't believe it. Even without a guest, we somehow were able to fill all the time. So we need to wrap things up. Pam, you've been waiting patiently. So tell us what you're working on and where people can find out more.
All good. And you know what? We got a really cool show. Friday nights, we are broadcasting live, and that's at 9 p.m. Pacific time. So if you're in other places in the world, you want to translate that, we go out to the Everyday Spacer YouTube channel, the Facebook page, and we found a new project. It's New Particle Search at CERN. And we're going to start off on Friday the 25th. Just a couple days from now. And I have a feeling, because it's so juicy and it's so beefy and it's so interesting, we're probably going to have more than one part. So we'll have possibly a series of them. And you know what? We really love to bring people onto our lives with us. If we don't have a guest, we come up with something like a citizen science project, like Friday will be. And if you want to show up with us, we would love that. We also have twice a year, we're going to have an open mic night. And we started something last week. It's listener questions. So we get questions from the audience and we try to answer them. So that's it.
Very cool. Chris.
Hello, I'm Chris Carr, and if you want to follow me on social media, I'm on Twitter at @TheRealCCarr.
Perfect. And we go into what you're working on every week, but you're still just working on research.
I'm working on my thesis.
On my thesis. Yeah. Yeah. I anticipate that's going to be the answer for until you get that doctorate, which is now locked in now that you're part of the show, of course.
I'll just have a button when I press it. Says I'm working on my thesis. So
I'm working on my thesis. Yeah, that'll be your Twitter. That'll be your Twitter bio. Alan, what are you working on, and where can people find it?
Yeah, same as usual. New content for Urban Astronomer at urban-astronomer.com. Getting back into writing actual news articles, as well as putting out more podcast episodes, which you can subscribe to from the website. Or you can find me on Twitter at UAstronomer if you want to hear my crazy political views. With some astronomy bit in there, so it's not a total waste of your time.
All right. Fantastic. Well, thanks, everyone. Of course, I'm Universe Today and all the things. I'm sure you can find that. Thank you, everyone, for joining us today. Really appreciate it. Thank you to my co-hosts. Thanks to everyone watching us on YouTube and Twitch. Thanks to all the moderators. Thanks to Nancy for organizing things behind the scenes. And thanks to Pamela for engineering the show. Despite all of the trouble that you went through, we really appreciate
today was magical.
Yeah, you going through it, all of the MacGyvering that brought this show together.
Yep.
Yeah. Man, do I appreciate the fact that you're here. All right, Thank you, everyone, and we will see all of you next week.
Bye-bye.